Hello everyone. It's a great privilege to be able to present this lecture to Colombo 2020. I'm very sorry that we're not able to meet in person, but I hope that wherever you are in the world, you'll be able to gain some benefit from the conference. And maybe this format of conferences will enable us in the future to have the benefits of dialogue without so much use of fossil fuels for traveling. In this lecture, we're thinking about embedded retaining structures, and in particular, what we can learn from some failures of that type of construction. So we're talking about lessons learned from failures of embedded retaining walls. By embedded retaining walls, we mean walls that penetrate into the ground, usually built before excavation, which gain some of their support from the passive resistance of the ground in front of them, something like that. They might be slurry trench or diaphragm concrete walls, heavily propped in this case. Variety of walls on this photograph with sheet pile walls along one side, some secant pile walls, interlocking piles there, anchored at the back, non-interlocking contiguous board pile walls at the side. Here the secant pile walls are anchored. And here again, we see deep diaphragm walls, concrete diaphragm walls with this time a sheet pile cofferdams built above them. Eurocode 7 presents these diagrams to indicate mechanisms by which retaining walls might fail. During this lecture, we'll discuss case histories which illustrate the examples ringed in red. And I hope we can pick up some lessons from these failures. Firstly, that we must always remember our basic engineering disciplines, drawing to scale and looking at those drawings to see what they tell us, being very careful about vertical datums and careful checking, preferably by an independent person. Think of the big picture, not just local details. Designers must be brave enough to be afraid and communicate very clearly. Remember that water is often the driver of problems. Avoid or take very great care with any elements in the structures that might be brittle. And remember that even for vertical embedded walls, vertical equilibrium is important. In the first example, we consider a tide wall of this type. Analyzed using active and passive pressures as if the tie were a rigid prop. It relates to a quay wall which was built in the early 20th century by placing steel stanchions into the ground and then bringing up fill either side of them as concrete arches were placed between the stanchions, an unusual way of building an embedded retaining wall. Here's a cross section. You can see that the wall is tied back by steel tie beams to concrete anchor blocks. This was a wet dock, so the tide would be taking water level up and down. But during the life of the dock, it was used as a dry dock. And for this purpose, a large berm was built in front of the wall so that the dock could be dewatered. Subsequently, it was to return to use as a wet dock. The berm was to be replaced, and it was decided that it would be stable with a small berm left at the base, as shown there. So the design was to proceed on that basis. The geology had a firm alluvial clay overlying stiff clays and stiff glacial materials. One of the issues, I think, of this project was that there were 4 different ways of characterizing vertical dimensions. One could use meters below the quay level or meters to the national datum, ordnance datum. Because it was a marine job, lowest astronomical tide might be the datum. Or you could measure upward from the dock floor. And it seems likely that some confusion between these different systems affected the design. The analysis assumed active and passive wedges in front of the wall, active and passive pressures, and on that basis, it was concluded that the small berm was adequate and dredging could proceed. So dredging started to take place in front of the wall, and a crack appeared some distance back behind the wall. I want to say that that is the time at which the designer and engineers involved should be concerned. Don't pretend it's a non-problem, but try to investigate, get in quickly and sort out the problem. And communicate very clearly. Conversations, or other communications, and especially any advice that's given. I'm not sure that that was done. And as a result, dredging continued and the crack got very much bigger. It was clear that the wall was on the move. Well, what was happening here seems to be that the crack was forming just behind the anchor blocks. That wasn't very obvious from quayside level, of course. And the mechanism for failure, rather than being the one that had been analysed, was actually an overall failure, taking in the anchor block. If you carried out a finite element analysis, it was fairly clear that that type of mechanism was going to be the critical one. The anchor was not all that long, and even a slope stability analysis would have shown very low factors of safety for that situation. So what had to be done was to backfill rapidly in front of the wall because the dock was booked for incoming shipping, and a new wall was rapidly built using steel pipe piles, very expensive remedial works. What do we learn from this? The importance of drawing to scale and looking at the drawings to ask, is this a reasonable design, a reasonable concept? Be very clear about datums for vertical dimensioning, and checking preferably by an independent person. Think of the big picture, think of all the mechanisms involved, not just the ones that handy software might choose to analyze. Be brave enough to be afraid. If something seems to be going wrong, get in quickly and sort it out. Communicate very clearly. And remember that water may be the driver, low spring tides in this case were the causes of the movement. The next example shows a case in which the tie supporting an embedded wall was breaking. It relates to another quay wall. You see it here under construction, and the intention was to bring the fill up behind the wall to provide a quayside. So here's a cross-section of the intended design. You can see that the wall was to be tied back to an anchor wall, some considerable distance behind it. Here's the original riverbank, and fill was to be placed behind the quayside, behind the wall. The type of wall was so-called Combi wall, with large diameter pipe piles and sheet pile sections placed between them. The tie rods were 75 to 100 millimeter diameter high tensile steel bars fastened into the pipe piles by being embedded in concrete, and they had a big nut on the end of them and a large washer to hold them into the concrete. Here you see the wall at a later stage of construction. And here is one of the anchor bars coming out of the back of a pipe pile. Well, the filling was completed, and shortly afterwards, the wall began to fail in one location particularly. So the contractor excavated down behind the wall to see what was going on. It became clear in that excavation that there was a construction problem, and some of the tie rods were pulling out of the combi piles. Probably, maybe the nut was not properly secured, or perhaps the washer was missing, and the tie rods were pulling forward. So to remedy that, it was decided to weld some wings around the combi piles, and with a little vertical web also on the side of the pile, and then to weld all that onto the high tensile steel bars. Here you see the construction with the wings and the webs welded onto the steel bars just there. The consulting engineer was questioned whether this design was a good one. He was concerned about the welding of high tensile steel bars, but he and the contractor were assured by the manufacturers that it was possible to weld these bars, and so the construction went ahead on this basis. And they filled again behind the wall. Again, it failed. When they dug down again, they found that the bars were starting to break, very clean break, just at the back of those wings, at the back of the welding. What was happening was that the process of welding had made the bars brittle. They'd had hydrogen embrittlement, and they were snapping off, although 100 millimeter thick steel here, but they were snapping off in a very simple manner. There's another one. You can see the break there between where it's pulled away from the pile. The bars had a casing around them, which was intended to allow for settlement of the fill. So the bars should be placed at the bottom of the casing, and maybe they were, but the fill had settled and was now pulling down on the bars. So the bars were being bent downwards. Now, I suspect that is not an unusual situation. When bars are placed in this way, they probably get bent, but that doesn't prevent them operating in a tensile manner, which is their main purpose, unless they have become brittle, and then the bending breaks them and they can no longer perform as tensile members. So what do we learn from this? Again, be brave enough to be afraid. If you suspect that something may not work properly, be very clear and pursue that to the end. At the very least, communicate your concerns extremely clearly. Put them down in writing. Don't allow anyone to be unsure that you object to what is being done. And of course, avoid brittle elements in the structures. I don't have photographs for the next example. It involves the failure by simple rotation of a propped wall. Quite a small wall, a sheet pile driven through 3 meters of fairly loose fill into dense sandy gravel. The design was carried out using active and passive pressure diagrams with a factor of safety of 2 on the coefficient of passive pressure. No water involved in this one. On that basis, it was concluded that a penetration of 0.65 meters into the dense sandy gravel would be adequate. So the wall was built to be 3.65 meters long. In practice, what happened was that the gravel surface in some places turned out to be slightly lower, only 0.2 meters. And the result of that was the wall failed by rotation. The difference in level probably wasn't enough for a contractor to really notice it. What's happening here? Well, if we had designed that wall for a factor of safety of 1, it would have had a penetration of about 0.45 meters. The design required it to have a penetration of 0.65 meters, and we'd have got much the same design if we'd designed to Eurocode 7 with 1.25 on tan phi. But in practice, what happened was that the surface of the gravel was 0.2 meters lower and the wall failed. Eurocode 7 has some thinking about this. It says that in ultimate limit state calculations, in which the stability of the retaining wall depends on the ground resistance in front of the structure, the level of the resisting soil should be lowered below the nominally expected level. And it goes on to say that if you're building a cantilever wall, you should assume the ground level to be 10% lower 10% of the height of the wall, that is. Or for a propped wall, you take 10% of the distance below the lowest prop, and you design for a slightly more adverse geometry than you're really expecting. If that had been done in this case, then the wall would have been deeper, and that failure would have been avoided. In fact, it would have been possible to excavate down to an additional 0.45 meters below the 3 meters expected before failure would have been likely. And I think at that point, it's quite probable that a contractor would begin to say, this is different from what I expected. It's interesting to note that you can't readily achieve the same effect by simply increasing factors of safety. Even with a factor of 3 on KP, you don't get the same depth of wall. So the important point to note here is that in design, safety allowances should be made in the geometry of the construction, as well as in the material factors or other factors of safety. There are several lessons to learn from the next example. In particular, the importance of vertical equilibrium in the design of embedded retaining walls. This photograph shows a site adjacent to the River Thames in London. The Thames is on the right here. On the left is an old dock which was out of use and had been silted up over the last 100 years or so. So it was filled with extremely soft, recently deposited materials. Attempts to measure its strength in boreholes gave very low values. You can see here that there's about 10 meters of the soft material. So low, in fact, that the designers didn't really believe them and chose to use strengths measured in other nearby alluvium, which was probably slightly stiffer. The first intention for this site was to build an earth bund across this opening here and to fill behind it, but the bund slipped into the river, and so it proved necessary to have a retaining wall. And in order to do that, an access way was constructed using this double skin cofferdam, which succeeded in providing an access way, but actually moved 10 meters towards the river during its lifetime. You can see that the materials are extremely soft. The intention was to build a sheet pile embedded retaining wall here, topped by steeply raking pipe piles. You can see here the 10 meters or so of alluvium behind it, and it was intended to place fill over it to bring the quayside up to level. Here you see the wall under construction. Fill is being placed behind the wall, but in front of the wall here, the ground is rising up and the wall is rotating in a horrible manner. Further along, you can see the pipe piles just hanging in there, but some of the wall has completely collapsed and the piles have disappeared into the ground. Well, what was going on here? Because it was recognized by now that this was a difficult site, the displacement of the sheet pile wall was monitored. You can see here the profile of displacement, initially vertically upwards, and then eventually downwards, exceeding 5 meters of horizontal movement before it eventually collapsed. So the movement was initially upwards and outwards until eventually the pipe piles buckled by being bent too much. In the analysis, the effect of the pipe piles was assumed to provide a horizontal force to support the sheet pile wall. But of course, for steeply raking piles, there would be a vertical component to that force, and that has to be balanced by taking a vertical force down the sheet piles and achieving embedment towards the base of the piles. Unfortunately, that hadn't really been thought through, and it was the lack of sufficient embedment that allowed the vertical movement to initiate the final collapse. Vertical equilibrium was important. What do we learn from this? Firstly, understand the history of the site, especially recently deposited materials, and don't discard very low measured values. Sometimes values can be so low that you can't measure them even. Watch out especially for strengths of critical zones of material. And for retaining walls, remember that vertical equilibrium is important. The final example relates to the collapse of the Nickel Highway Station in Singapore in 2004. There are very many lessons to learn from this very unfortunate incident. In terms of the failure mechanisms, there was a bending failure in the wall, an issue of toe stability, and most critically, issues about the strength of the strut supports. This is the station under construction. The excavation was about 30 meters deep in Singapore soft marine clay, about 22 meters wide. And you can see that it's adjacent to the Nickel Highway, the major highway from the center of Singapore to the airport. And at the end of this section, there is a launch shaft to take a tunnel boring machines, which we're going to work out under the river in that direction. Within a few moments, that construction turned into this horror. The road has collapsed, but most importantly, the excavation itself is in a state of terrible collapse. 4 people very sadly were killed, and it's really amazing that there weren't more fatalities. If you'd gone down inside the excavation at an earlier stage, you'd have seen something like this. At upper levels, there were single struts spanning between the diaphragm walls, but then at lower levels, there were strut pairs. Strut pairs were designed to bear onto the retaining walls, the diaphragm walls, by steel whalers here, and the load is spread onto the whalers by splay beams. The excavation was built through about 40 meters of soft clay, mainly marine clay, by first of all sinking the concrete diaphragm walls, and then a king post was driven to support the steelwork inside. 2 layers of jet grout were installed to provide propping at a low level, and the permanent piling for the station was installed. And then the excavation began, installing struts as each level was excavated. And we pick up the story when the 9th level of strutting has been installed and excavation is underway for the 10th level, the upper jet grout level having been removed. Reminder of how this station looked. There's the launch shaft at the end there. And in plan, here's the launch shaft at the 10th level, or rather at the 9th level, we see strut pairs spanning across between the walls. This cross section was instrumented. There's an inclinometer in the ground there, an inclinometer in the wall there, and strain gauges on the struts. This is notably, this is the north side, this is the south side of the excavation. Issues considered by the public inquiry were these. Firstly, the factors of safety were lower than code requirements. The wall was rather weak. This was a geotechnical issue arising from the geotechnical analysis. There was inadequate toe penetration into the strong old alluvium materials. The quality of the jet grout was very questionable. No check on water pressure beneath the excavation, an issue about excavated bay lengths, which I'll explain later. The strain gauges on the struts probably were incorrect, and the issue of heave of the king posts was much debated. Most critically, the strut connections were not adequate, and this was a steelwork error. My belief, however, is that if any of these errors had been avoided, the excavation probably would not have failed. It very nearly succeeded. So looking at those issues, the factors of safety on being lower than code requirements, the analysis was carried out using finite element methods with unit factors on soil strength and soil resistance, factors of 1.2 on the wall reinforcement and the steel propping. This was justified by saying that it was temporary works that were being designed. The public inquiry concluded that full code values of factors should be maintained in temporary works. This somewhat reflects the thinking of Eurocode 7, which says that less severe values may be used for temporary structures or transient design situations where the likely consequences justify it. It's all about consequences, not about the time period for which the design must succeed. The Singapore Code of Practice required a check for loss of a single strut. This wasn't done at a critical stage of the design checking. If it had been, it would have increased the factors on the strut to about 1.4, which might have been enough to prevent the failure. The wall was perhaps too weak for a geotechnical reason. And it's the reason related to how you model undrained strength in a finite element analysis. This graph shows shear stress against mean normal stress in the two-dimensional analysis, and all the analysis was two-dimensional. And here's the more Coulomb envelope. The model used was a simple linear elastic more Coulomb model. And I want to say that anyone doing geotechnical finite element analysis must understand this level of geotechnics. So in a more Coulomb model, it was assumed that the behavior below the envelope was linear elastic. The analysis starts from a Keynote condition in the ground, and undrained strength was reasonably well known from test results. If you carried out a laboratory triaxial test, you'd get an undrained stress path which looks something like that, where failure would occur on the more Coulomb envelope at the undrained strength, as pore water pressure develops in the soil as it is strained. However, the analysis assumed linear elastic behavior in which the undrained stress path goes straight up the diagram and failure occurs at a much higher apparent strength, overestimating the strength of the soil by about 40%. That was known as method A. And the difference between the two approaches is the development of water pressure in the soil. It would be possible to use method B, in which the undrained strength is imposed correctly. Water pressures wouldn't be right, but the strength would be critically. The Plaxis manual at the time advised the use of method A. The design intended that the walls would penetrate 3 meters into the very stiff, strong old alluvium at the base beneath the soft clays. And on the north side of the excavation, the actual profile was fairly similar to this at the monitored cross section. So looking at results for the north side, the predicted displacement of the wall using method A is shown here in green, with about 100 millimeters maximum displacement. But the measured displacements were the brown ones, roughly double the prediction. If method B had been used, the displacements would have been predicted more or less correctly. Critically, if we look at the bending moment diagram, method A gives the green curve for which the design envelope was prepared for the diaphragm wall, whereas method B would have given double the bending moment, indicating that the wall as designed was not really strong enough. So that was for the north side of the monitored section. On the south side, the displacements were much larger, probably a plastic hinge formed, and that weakness of the wall may have been critical to that. The important effect of that would be that when the steelwork was starting to fail within the excavation, the wall on the south side would not be able to transfer load between the different prop levels. But why were the displacements larger on the south side? This relates to toe penetration into the old alluvium, which was not checked during construction. There were supposed to be 3 meters of penetration. In reality, the ground profile varied across the excavation, and on the south side, the wall hardly penetrated into the old alluvium. The result of that was much larger displacement. And this really is a communication error. The design assumed 3 meters of penetration, but the guys on site didn't know that and built to a depth. What about the jet grout? The strains in it were much too high. Here's the jet grout strut here. And as you've seen, the displacement on the north side was very little at the level of the jet grout, very considerable on the south side. Now, if you test jet grout in laboratory tests, here's a graph of strength against failure strain, and you can see that generally it fails at around 1% failure strain in a brittle manner. Once it gets to its peak strength, it's destroyed. However, it was modeled as a ductile material, critically. Now, if you look at the actual displacement measurements, you can see that the strain between the two walls amounted to about 2%, some weeks before the failure. So clearly the jet grout was overstrained and had probably lost all its capacity to provide a strut. Water checking. The computed, there was a piezometer located below the excavation here, and the red line here shows the computed water pressures as excavation took place. The blue dots were the measured water pressures, which look as if they're about to exceed the computations. However, at that point, the piezometer was lost and it wasn't replaced. So we don't really know what the water pressures were beneath the excavation, but it's pretty likely that they were in excess of the assumed values. Excavated bay length. Well, here is level 10 in plan. Here is a section up the center there. The method statement said that only 4 bays would be open at any one time of excavation before the struts were properly engaged to provide protection. So to get to 6 bays, these struts have to be fully in use. What was actually done was that 8 bays were open and the struts at this end still had not been engaged. We tried to analyze what the effect of that would be in a 3D finite element analysis. And the conclusion of that was that adjacent to the excavation face, you get about a 37% reduction in strut force compared with the 2D design analysis, about 10% on the next bay, nothing on the rest. So if only 4 bays had been open, the strut forces would have been significantly reduced and the excavation probably would not have failed. Sadly, the strain gauges were probably incorrect and reading too low. This was unfortunate because the engineers relied on them and concluded that the excavation was safe, even though they could see that the steelwork was deforming quite badly. Heave of the king posts was raised as an explanation. This diagram is from a finite element analysis. It's a fairly realistic depiction of the deformation at the time before the collapse, without any exaggeration on the deformation. You can see that the ground is being forced upwards as the wall is moving inwards, probably taking the king post up with it. And it was suggested that this would cause a cause of the way that the whalers collapsed. However, the public inquiry concluded that this was not a cause. It might have been part of the final mechanism of collapse, but was not part of the cause. But most critically, the steel strut connections were under-designed. The system of connection showed the steel props bearing on a whaler, which was stiffened by channel sections. So here we have, first of all, the web of the whaler and the web of the steel strut, and those two interact very critically at a point there. The strength of that interaction was overestimated by 50%. And this meant that the stiffeners, the channel sections here, were overloaded critically. Recognition of that problem would have led to a more robust design. Another major issue was that, as I mentioned, the steelwork design assumed that there would be splays spreading the load onto the whalers. Now, if we look at the photograph at level 9, this strut pair here has splays, but this one doesn't, and that doesn't, and that doesn't. The splays are missing. The design assumed that of the force coming along the strut, 2/3 of it would be taken directly through the connections in the whalers, 1/3 would go down the splays. If you miss the splays out, the strut connection here is overloaded by 50%. You can see here that the original design had little plate connections in it, plate stiffeners rather, not the channel stiffeners that were finally employed. And so you see that without the splays, with the channel stiffeners are now being bent down as the failure is starting to take place. Looking at the drawings in plan, you can see that probably the splays have been missed out because there isn't room for them. But this again is a communication error. The steelwork designer assumed there were displays, the drawings don't show them, and the construction didn't have them. So the strut connections were under-designed, and critically, they were also brittle. Here we have a finite element analysis of the strut coming to the whaler with the channel sections here and the wall. You can see the way the channel sections are bending down as they're overloaded. The graph here shows what happens to the force in the being taken through and into the wall against the displacement of the strut as the strut moves towards the wall. The force in the whole whaler connection builds up rapidly, reaches a plateau, and then as this bending starts to take place, the force drops down rather rapidly. And you see exactly that sort of bending was taking place. So the capacity of the connection was rapidly diminishing. Interestingly, the original plate connection design would give a graph like this, slightly lower peak, but a much less brittle behavior. And it's probable that if that had been used, the engineers would have had time to implement remedial measures when they saw failure beginning to occur. So very sadly, within a matter of minutes, that situation turned into disaster. Ground movement caused a fracture of a gas main, which exploded, and the site collapsed very rapidly. In geotechnical design, there are many things which we do not understand well and cannot compute accurately. But if we can prove that an equilibrium set of stressors exists, including vertical equilibrium, which does not exceed the strengths of the materials involved, soil and structure, allowing for water pressures in the soil, designs will generally perform safely. But beware of brittleness. Thank you for listening. I hope you enjoy the rest of the conference.